Okay, everybody. I just want to take a couple minutes and go over the momentum practice quiz that you did either on Wednesday during class if you're in the morning or on Thursday if you're in the afternoon class. So let's go over this. This is the first one. Now, all these problems deal with momentum, impulse, and the conservation of momentum. Okay, so the first one is asking you for what is the change in momentum. Now, the first thing you have to remember is that momentum is represented with a lowercase p in equations. Okay, you can see right here this delta p. That means the change in momentum. So that's really what you're looking for. So you're looking for how much did you add to it, because if you look at the speeds, it's getting faster. If it's going faster and it's gaining velocity, it also should be gaining momentum. Okay, so momentum is always mass times velocity, so the change in momentum would be the mass times the final velocity minus the mass times the initial velocity. Remember, these little f's mean final and these little i's mean initial. There's no I and f near the masses because the mass doesn't change. Okay, so if you look at it, we have our masses in kilograms and our speeds in meters per second. Okay, and it's just the difference of the two. And you should get 5,500 kilograms meters per second. Now, I put in the positive direction because I didn't really specify what direction it was going in, but you do know that it's increasing. So a way of writing it in a sentence is the momentum of the meteor increases by 5,500 kilogram meters per second in the positive direction. It's gaining that much. Okay? Now, the next one, number 2, an 800 kilogram satellite traveling at 30 meters per second up. I meant to say up. I needed to add that little bit in. Hopefully you heard me in class when I said it. Inside the Earth's atmosphere, ignites its boosters and accelerates for 0.65 seconds. So it's going to accelerate upwards, so it's going to gain speed. So you know that if it's going to gain speed, that your answer should be larger than 30. Okay? So when we look at this, what's really making it gain speed is the thrust that it exerts on itself. Okay, 15,000 newtons. But since it's going away from the Earth, it's being opposed by the weight of the satellite itself. So its own weight is actually trying to stop it from moving forward. Now, how do you know this is an impulse problem? Look at what you have available. You have mass, you have velocity, you have time, and you have a force. So you have forces, times, masses, and velocities, and you're looking for velocity. So an obvious way to look at this would be, okay, those are the things I have. The equation that I have that deals with those is F times time equals mass times the change in velocity. Now, what's unfortunately about this equation that we have right here, it's not specific enough. We have to change this F into what's more specific for our situation. Well, remember, F always really stands for driving minus retarding. Well, what's driving this satellite forward is the thrust that the booster rockets are exerting upward. What's trying to hold it back is the weight of it. So instead of having this F, a better way of describing it would be thrust minus weight. Okay, times the time equals mass times the change in velocity. Now remember, what you should always try and do first is you should always try and do the algebra first. So if you look at this, I divided by m to get it to the other side, and then I added vi to get vf alone. And once you do that, it's just plug and chug. You should end up with 35.8. So this number right here should say 35.8. I messed up on my calculator the first time I did it. Okay, so this number right here should be 35.8. So let's actually fix that. So I'm just going to write right over top of it 35.8. Okay. Most of you did really well with that problem after you understood where the weight came in. Okay. Now the third problem, now that is a conservation of momentum problem. Okay. Now conservation of momentum deals with two things interacting or colliding. So I gotta fix that right there. Hold on one second. I gotta fix my number right there. So, whoops, don't want that. I don't know what that was. Sorry about that, everybody. So when we look at this, the fire extinguisher is being strapped to the top of a skateboard, and it's sitting idle. And inside this extinguisher is 2 kilograms of halon that is allowed to expel from the canister at a speed of 50 meters per second north. So before the interaction occurs, nothing has momentum. That's why these are all zeros on this side. Remember, initially there's nothing going on. There's no speed, so there's no momentum. Afterwards, if you're able to, I'll zoom in a little bit. When you look at it, 2 things have momentum. Those 2 kilograms of halon are getting expelled backwards at 50 meters per second. So therefore, the remaining mass, which is the extinguisher and the skateboard, have some velocity of their own the other direction. It's very similar to a bullet and a gun, a cannon and a cannonball, anything like that. There's always a recoil. So this is like the bullet, the halon, and the extinguisher and the skateboard is just like a gun. Okay, so what I did, I moved the 2 kilograms times 50 meters per second to the other side, and I solved for V1F, and I got 9.09. Okay, let me fix that. I'm having a terrible time with my numbers today. 9.09. So that means that the extinguisher and the skateboard are going 9.09 meters per second south. Okay? So even I need practice with my calculator once in a while. Okay? So remember, that is the reason why I use that equation there is because if you look in the problem, there's nothing mentioned about forces or times. So you automatically know that the FT equation that you have won't work because you don't have what you need in order to solve for it. Now the last one we're going to look at is the graph question. Now this one was a little tricky for some of you. So look at it. You have 2 graphs. One of them represents a baseball and a bat. One of them represents a tennis ball and a tennis racket. Now the difference between these 2 graphs, when you just look at them, if you just look at the 2 graphs, you'll notice that one has a higher peak force and one of them has a lower peak force. The first one, has less time. B has more time. So if you think about it, between those 2 interactions, which one is going to be a quicker interaction between the objects, the ball and the bat, or the racket and the tennis ball? Well, if you think about it, a baseball bat is very rigid. Okay, it doesn't have a lot of flex to it. So when it comes in contact with the baseball, it's not going to happen for very long. It's going to be a very quick hit, and it's going to be recoiled off into the outfield. A tennis ball is very flexible, and so is the racket itself. So because of their flexibility, the tennis racket's going to act like a cushion that basically will catch the ball and then throw it forward. Because it occurs for such a long time, because of that flexibility, the force on it goes down. Okay, so B would actually represent the tennis ball and the tennis racket because it takes a long time for the interaction to occur, so the force is shorter. A is the baseball bat because it occurs very quickly, so the force it takes to make it happen is very high. Okay, it's very similar to no airbag and an airbag. A would represent, very similarly, a car without an airbag. B would represent a car with an airbag. Airbags are meant to give you a cushion to prolong the time it takes you to come to a stop, reducing the force. Okay? Now, if they both have the same mass and the same change in velocity, what must be true? They must have the same change in momentum, regardless of how they're forced. If they have the same mass and the same change in velocity, they have the same momentum change. Okay? Sometimes that's difficult to understand. You would think that because there's a larger amount of force from a baseball bat that it would have a bigger momentum. That's not necessarily true. It's all about mass and velocity for that. And I kind of already described why the graphs are different. It has to do with the amount of time that the contact takes place. Rackets have a longer contact time, so they have a smaller force at their peak. Okay, I hope this helps. If you have more questions, obviously come ask me, but I really hope this is helpful to you.